Hey, welcome back to the Intro to Internal Combustion Engines. Today's lesson objective is to identify the basic components of a reciprocating internal combustion engine. Let's quickly review a few terms associated with the piston cylinder assembly. We'll start out by drawing a piston cylinder, and you can find this in your textbook in figure 13.1. Now, at the top of that cylinder, you have an intake valve. That intake valve is going to open to allow an air-fuel mixture, or air, depending on the type of engine, to enter that cylinder. You also have an exhaust valve that's going to open up to allow exhaust gases to flow out of that cylinder as necessary. At the top, we are going to depict a spark plug for a spark ignition engine or a fuel injector for a compression ignition engine. Now, that being said, you can have direct injection in a spark ignition engine, but for the purposes of this course, this will represent a spark plug for spark ignition and a fuel injector for compression ignition. Now that cylinder has a diameter, which we define as the bore. And within that cylinder, there is a movable piston. When it's at its utmost position, we refer to that position as top dead center. That position at top dead center creates what we call the minimum volume, the clearance volume, or the top dead center. You'll hear all three of those terms used interchangeably. Now, during the intake stroke, the movable piston will move down and the intake valve will open, allowing air fuel to enter, or it will move down to this position during the expansion stroke or the power stroke, which you'll learn about later. Either way, at the bottommost position, we refer to that as the bottom dead center. Now, the distance that the movable piston travels from top dead center to bottom dead center is what we refer to as the stroke. And the volume contained therein is what we refer to as the displacement volume. Let's take a look at that in equation form, in equation 13.1. So the displacement volume is equal to the area of a circle, 1/4 pi diameter squared, which in this case is the bore squared, times the height of the cylinder, which is only the height of the stroke for the displacement volume. So when you're talking about engine sizes, for example, my Camaro has a 5.7 liter engine, or my Mini Cooper has a 1.7 liter engine, you're referring to the number of cylinders times the displacement volume of each one of those cylinders. And you'll find that in your textbook as equation 13.2. Don't confuse that with the maximum volume. The maximum volume, or the volume bottom dead center, is equal to this displacement volume plus the clearance volume. This is a common error. This is equation 13.3. Let's talk about compression ratio, a term we're going to use throughout this course, and you've probably heard before. The compression ratio is the ratio between the volume max, the max volume, the volume bottom dead center, and the clearance volume, the volume top dead center. That's equation 13.4 in your textbook. Let's discuss how a reciprocating internal combustion engine translates the linear motion of the piston to the rotational motion of the crankshaft. So I direct you to your textbook to figure 13.2, which shows a depiction of this process. Let's orient ourselves to this and highlight a couple aspects, and then we'll show an animation. So we have a cylinder, a piston within that cylinder. That piston is connected to the crankshaft via the connecting rod. And notice that connecting rod is connected to the crankshaft off center from the rotational axes, or the longitudinal axes of the crankshaft. Therefore, when the piston moves between top dead center and bottom dead center in a linear fashion, it causes the crankshaft to rotate about its longitudinal axis in a rotational manner. This animation, I think, makes it a little bit clearer how that linear motion translates or converts into rotational motion of the crankshaft. But that depiction of a crankshaft is very simplified. Let's show you a quick, let's quickly go over a real crankshaft. This is a real crankshaft, and you can see the rotational axes, or the longitudinal axes, from the pulley end to the flywheel flange. We'll talk about what a flywheel is here momentarily. You can see where the connecting rods connect to the crankshaft at the rod bearing journals. And each of these segments are connected via the main bearing journals along the longitudinal axis. Now those holes contained within allow oil to flow through for lubrication and some cooling effect. What I really want to draw your attention to are these counterweights that you don't see in this CAD model. And those counterweights serve two purposes. One, they reduce the bending load on the crankshaft, and two, they reduce the vibrations. Let's see it in action. So this is a 4-stroke inline 4-cylinder engine. You can see that each cylinder has its own piston. Each of those pistons have their own connecting rod that connect them to the crankshaft, and the crankshaft connects all those pistons together. Note that piston 1 and piston 4 are in phase with each other, and piston 2 and piston 3 are in phase with each other, but they are out of phase 180 degrees from pistons 1 and 4. This is done for vibrational purposes. Now note, each of these cylinders, even if it's in phase in motion with another cylinder, is in a different stroke, and we'll talk about that later on. Now you can see the intake and exhaust valves moving as part of a coordinated dance, and they're moving via these rocker arms and these push rods. We'll talk about that in a subsequent slide. In order to keep that all timed properly, you use a camshaft with cam lobes that push up on these lifters and push rods, and they're kept in time with the crankshaft via this timing chain. Let's dig a little bit deeper into the terminology associated with a push rod versus a dual overhead cam engine. Now, this isn't meant to make you an expert, just to give you familiarization. If you want to learn more about internal combustion engines, I recommend taking the mechanical power plants course in the automotive track. Now, let's start off with a push rod, since we just saw that. The traditional engine design, where you have the piston cylinder connected to the crankshaft via the connecting rod. And at the end of that connecting rod, you have a crankshaft sprocket that uses a timing chain or a drive chain connected to the camshaft sprocket, which is attached to the camshaft. The camshaft has lobes or cams machined on the surface that, when in the upright position, push on the tappet, which in turn pushes on the push rod. The push rod causes the rocker arm to pivot about its pivot point and compress the valve spring to open the associated exhaust valve or intake valve. The valves are spring-loaded in the closed position for obvious reasons. Now, more modern designs use an overhead cam or a dual overhead cam, depending on the application. There are some limitations to push rod engines that can cause the rods to bend, and it just increases mechanical complexity and introduces more points for failure. In a dual overhead cam, in this case, or an overhead cam, the push rods are removed and the cams are repositioned directly over the valves. The valves are still spring-loaded closed. You still use a camshaft sprocket and a timing chain or a drive chain to connect to the camshaft sprockets. You've just eliminated the push rod and rocker arm aspect. Now, in this particular engine, you have 4 valves per cylinder, so 2 intake and 2 exhaust. That allows for a more powerful engine in its size, more air and fuel to get in, more exhaust that is required to leave, and so you're going to have a higher performance engine. To reduce some of the complexity of the machining of the cam, typically in a 4-valve per cylinder engine, you will have 2 overhead camshafts, 1 for intake, 1 for exhaust. That can be changed depending on your needs. The last thing I want to draw your attention to is the flywheel. And the flywheel stores energy required to keep the engine turning between power strokes. Typically, there's only 1 or 2 cylinders producing power at a time, and you want that to be smooth and consistent in your vehicle. In fact, in this 4-cylinder engine, only 1 of these pistons will be producing power per stroke. Let's talk about the difference between a carburetor versus a fuel injector. So here we have a 4-barrel carb, so it has 4 carburetors combined into one. This is for a high-performance vehicle. Let's take a look at just a single barrel carb. This cross-section from Wikipedia Commons that is a little bit easier to understand. So as I press down on my accelerator in my vehicle, it's connected via a mechanical linkage in older cars, and it will actually actuate this throttle valve. That throttle valve will increase the mass flow rate of air coming in to the carburetor. I hope you recognize this carburetor as a venturi. So the diameter of the carburetor narrows at the throat. So conservation of mass is going to tell me that the air must accelerate to adhere to conservation of mass. As the air accelerates, it decreases the static pressure. That static pressure creates a pressure imbalance, or essentially a vacuum, that draws fuel out of the float chamber. Now, this float chamber doesn't contain all of your fuel, obviously. It just contains a small amount of fuel. And using the same buoyancy principles as the float in your toilet, as the fuel gets diminished or used within the float chamber, the float moves down. It opens the float valve, And that allows the fuel pump to pump more fuel into this float chamber. Now, while this design is mechanically brilliant, it is not the most fuel efficient. So most modern cars, to optimize the fuel-air mixture, will use fuel injection. Now, there are two types of fuel injection in spark ignition engines. One is the port injection, and the newer design uses direct injection. Something like the new Ford F-150 EcoBoost engines use direct injection. Typically, well, not typically, all compression ignition engines, diesel engines, use direct injection. So, for a port injection, the fuel is injected with the air just prior to the intake valve, and in a direct injection engine, it is sprayed directly into the cylinder, and the air comes in as air only. Appropriate engine design to cause appropriate mixing and swirl are necessary to facilitate this, and what's made direct injection really possible in spark ignition engines as of late is really the computer modulated controls. This is a mass airflow sensor. So just like on your carbureted engine, you have a mechanical linkage to your accelerator. When you press down, it opens this butterfly valve that allows more air to come in. And you have sensors on there telling the computer the density of the air and the rate of flow of that air, so it can calculate the appropriate amount of fuel to inject, whether it's a direct injection or a port injection. Now, not all cars have this mechanical linkage. Most modern cars, in fact, the modern F-150, for example, this is an F-150 mass airflow sensor, has an electronically actuated butterfly valve. So there is no mechanical linkage when you press down the accelerator. It's all done electronically. Okay, that wraps it up. That should just be a basic introduction to your basic components of reciprocating internal combustion engines. If you have any questions, consult the book, check the internet, and feel free to contact your instructor. We'll talk to you later.